So today we will be solving the problem how to find a shortest path in a weighted, yes, in a weighted DAG. So you are given a source, for an example, the source is 0. Now you have to find the shortest distance from this node 0, for an example, say the node 3. So from 0 to 3, I can say that the shortest distance is definitely 6. How? 1 plus 4 plus 1. So there are weights on every edges. Yes, every edge has a weight. So if you can figure out any other shortest path, you can. But yeah, this will be the shortest path, which will have a edge weight of 6. Basically, you go from 0 to 4, 4 to 5, and then from 5 to 3, where the 0 to 4 is 1, 4 to 5 is 4, and 5 to 3 is 1. So the shortest path from the source 0 to the destination 3 is 6. So the question states, you'll be given a source. Yes, you'll definitely be given a source, and you need to tell the shortest distance from this 0 to every other node. Yes, 0 to 1, 0 to 2, 0 to 3, 0 to 4, 0 to 5, every other node you have to tell us the shortest distance. So since it's a weighted graph, the representation will change a bit. You have to store in terms of pairs. Previously you always stored like vector of int of adjacency, right? You stored vector of int of adjacency, or you were having array list of integers. Now instead of this integer that you did store, you will be storing a pair. Yes, you will be storing a pair. So this is how you're going to change. In Java also, instead of an integer, what you can do is you can store a class. I'll be showing you while I'll be coding this. I'll be showing you while I'll be explaining the code. Don't worry about that. But you will have to have a class pair like this, right? Where you define the pairs by yourself. So basically you need an integer in C++ and a class of pairs in order to store a weighted graph. So if I draw the adjacency list for 0, you know 0 is directly connected to 1 and the edge weight is 2. So you're going to store them in pairs. And which is the other adjacent node? That is the node 4. So the node 4 is having an edge weight of 1. So you simply store it. For node 1, which is the adjacent node, the adjacent node is not 0 because it's a directed graph. The only adjacent node is node 2 and with a distance of 3. Now for the node 2, which is the adjacent node, for node 2 the adjacent node is definitely the node 3 with a distance of 6. For node 3, which is the adjacent node, for node 3 there are no adjacent node. For node 4, which is your adjacent node, for node 4 there can be two adjacent node. One of them is 2, which is having a distance of 2, while the other is the node 5, which is having a distance of 4. Now for node 5, which is the adjacent node, for node 5 the adjacent node is node 3. So you can have the adjacent node 3 with a distance of 1. For all the nodes you can have the adjacency list like this. You can store pairs. Basically this is the adjacent node and this is the edge weight. So this will be your adjacency list for this given graph. Now in order to find the shortest path, your first task will be to find the topological sort for this given DAG. Now if you don't know how to find the topological sort for a given DAG, I've already explained two methods. One is the DFS method while the other one is the BFS method in my previous videos. So go back and watch those previous videos. You will get the method. Once you have seen the topological sort, you can come back and rewatch this. So basically you know that in topo sort we just did a DFS, right? We just simply had for the node started from 0 and it went on till 5, and if it was unvisited, if that node was unvisited, we called the DFS, correct? So let's do this. And we also had a stack. So let's have a stack. Along with this we also had a visited array. So let's have the visited array. And everything was marked as unvisited. So this is the first step to find topo sort. If you remember, we always declared a stack. We had a visited array which everything is marked as unvisited, and then we simply called the DFS function. So basically the first value of I is 0. Is 0 visited? Definitely not. That's not visited. So we call DFS of 0. Whenever we reach a DFS, please make sure you mark it as visited. Now what are the adjacent nodes of 0? That's 1 and 4. So there will be two different recursion calls. one will be for 1 while the other one will be for 4, but this will not happen. First this will happen 1, because always the first recursion call takes place. So DFS of 1 is called. Whenever 1 is called, please make sure it is marked as visited. After 1, what are the adjacent nodes of 1? So let's check it out. The adjacent node of 1 is 2. So let's have the DFS call for the node 2. So whenever you go to 2, again please make sure you mark it as visited. What are the adjacents of 2? So we can see the adjacents of 2 are 3. So we go to DFS of 3. So whenever you go to someone, please make sure you mark them as visited. So please mark 3 as visited. Do you find any other adjacent nodes for 3? We definitely do not find any other adjacent nodes. Thereby, we will not have any other recursions. Now, since we do not have any other recursions, I can say that the DFS call for 3 is over. Now, whenever a DFS call was over, you took that node and you put it into the stack for finding the topo sort. And I'll not be explaining why we did that, because I've already explained the intuition in that topo sort video. Now you come back, right? When you come back, 2 is also over, so put that. When you come back, 1 is also over, please put that. Now you had a 4 recursion call left, so what you'll do is, now you will have the DFS of 4 called. Whenever you have a DFS of 4 called, please make sure you mark it as visited. What is your next step? Which is the adjacent node of 4? I see one of the adjacent node is 2, but will there be a DFS call for 2? Definitely not, because 2 is already visited. So there will be no call for this 2, right? There will be no call because it's already visited. Which is the next adjacent node? As I can see that the next adjacent node is 5. So what you do is, please make sure that 5 is visited. Now whenever you go to 5, what adjacent node does 5 have? I see the adjacent node of 5 is 3. Do you do a DFS call for 3? Definitely not. Why? Because 3 is already visited. So I can say that the DFS call for 5 is over. Now when a DFS call for 5 is over, you don't do anything. You simply just take it and do this. You put it into the stack and you go back. Now when you go back, can I say that 4 doesn't have any other adjacent nodes? So the DFS call for 4 is definitely over. Now when it's over, you put that into the stack. Again you go back. Now whenever you go back, the DFS call for 0 is also over. So the DFS for 0 is also over. You can take that 0 and put it into the stack. So I can say that the topo sort for this given DAG is stored in this stack. So once that is done, this I will go to 1 and it will increase its value till 6 and everything will come as visited. So there will be no further calls and ultimately I'll get this topo sort. I did not explain topo sort in that much deep because I've already explained that in the previous tutorial. So once you have found the topo sort, what is your next step? The next step is very simple. Stack stores D4, right? That is last in first out. The first element in the stack will be 0. So you just basically start with that. But before that, just need to have one more data structure. Yes, you need to create one more array, distance array. And please make sure you create it of the size of the number of nodes. So let's create that. So if I write 0, 1, 2, 3, 4, 5, we have 5 nodes. And make sure everything is marked as infinity, where infinity can be a very larger value, which can never be your answer, right? It can be a very larger value. Since you're looking for shortest path, please store infinity as a very larger value. So infinity is stored. Now what is your source? Source is 0. Please make sure that the source is having the value 0 initially, right? Now whatever is your first element in your stack, please take it out. So please take the first element out in your stack, right? So node 0 has been taken out. Now at the first step, please check the value at 0 is non-zero, because what that means is you have reached 0. Yes, you have reached 0. Please check if the distance of node is not infinity, which will mean that you have reached that node. Yes, please do have a check. So distance, the node 0 is 0. Now from node 0, if I write 0, the distance taken is 0, which you can get it over here. The distance is 0. So I can say you took a distance 0 to reach the node 0. And that's very obvious, because if you start from source 0, if you want to reach 0, the distance taken will be definitely 0. What are its adjacent node? The first adjacent node that you encounter is 1. You can get it via accessing this dot first. And what is the edge weight? The edge weight is 2. So can I say if I took a distance of 0 to reach 0, and I'll take an extra distance of 2, which will make me take a distance of 2 in order to reach the node 1. Definitely yes. So can I see this? Can I see this? That the distance 2 that I am taking to reach 1 is actually lesser than infinity. Hence I got a better, yes, I got a better reach. I can update this to 2. Yes, I do update this to 2. Next step, which is the next adjacent node, the node 4. So can I reach 4? Definitely yes, because if I take a distance of 0 to reach here, and then I take a distance of 1, the total distance I'll take is 1. Now, is this better than what I have already taken? Yes, it's better than infinity. So please make sure you change it to 1. So I've made sure that I've changed it to 1, right? So once I've done this, are there any other adjacent nodes of 0? As far as I can see, there are no other adjacent nodes of 0. So what we will do is, we're going to wait. Yes, we're going to wait, and the node 0 is over. Now we will move to the next node, that is node 4, and we're going to again repeat the same task. So let's do it. Now when you go to node 0, now when you go to node 4, please make sure you check it again. Is node 4 non-infinity? That means you have reached node 4. If that is non-infinity, that means you have reached node 4. And what was the distance taken? 1. 1 is the distance that you took to reach 4. Now from 4, where can you go? You can go to 2. Yes. And if you decide to go to 2, what will be the distance taken? The distance taken will be 2. So what will be the total distance taken to reach 2? I can say 1 plus 2. That is a total distance of 3. Now what was the distance taken to reach node 2? Infinity. So can I say I got a better one? The distance 3. So I can replace infinity by 3. What is the other adjacent node? Other adjacent node is 5. So can I reach 5? Definitely yes, because it's an adjacent node. What is the distance taken? 4. So what will be the total distance? The total distance will definitely be 4 plus 1, 5. So in order to reach 5, I took something better, 5, better than infinity. So I'll replace over here by that. And does 4 have any other adjacent node? I see that 4 doesn't have any other adjacent node. So I can say that the task for 4 is over. So once the task for 4 is over, I'll move to the next node, that is node 5. So when I move to node 5, is that non-infinity? Yes, that's non-infinity. So I can say in order to reach this node 5, I will take a distance of 5, right? Now what are the adjacent nodes of 5? That's 3. What distance will you take? That's 1. So what will be the total distance? That is a total distance of 6. Now I am asking you a very, very simple question. If I'm taking a distance of 6, is that better than infinity? Definitely yes. So I just replace this with 6. Now does 5 have any other adjacent node is my question to you. Now the answer to that will be 5 doesn't have any other adjacent node. Yes, I do not see 5 having any other adjacent node. So I can say the task for 5 is also over. Now what is the next node that you get out of the stack? That's the node 1. So in order to reach 1, what is the distance that you took from the source? You can easily get it. The distance is 2. Now what are the adjacent nodes of 1? The adjacent node of 1 is 2. Now what is the distance that you are taking? 3. So let's have a 3. So what is the total distance that you will take to reach 2? The total distance that you will take to reach 2 is 5. Now I am saying that at 2 we already have a 3, which means you took a distance 3, and that's very obvious, because if you take this distance, that will be having edge weight of 1 and 2. That is what is stored here, the 3 distance. Now what distance are you taking? You are taking via 1, that is this path which is having 2 and 3. So definitely, since you are finding the shortest path, you're going to compare if this 5 is smaller than 3. Had this 5 been smaller than 3, you would have replaced it, no doubt in this. But since it is not, there's no need to replace it. Yes, there's no need to replace it. This is a simple check you need to do. You just need to compare with distance. If it is, then you replace. Otherwise, we are not going to replace. We're going to move forward. So, does 1 have any other adjacent node? Definitely not. So, the job for 1 is also done. What is the next node? The next node is 2. So in order to reach 2, what is the distance that you took? It's not infinity for sure. It's the distance 3. Now 2 can go where? 2 can go to 3. By how much? By a distance of 6. So if it decides to take a distance of 6, The total distance that it will take will be 6 plus 3, that is 9. So can it go to 3? No, it will not take this path because this path is taking a distance of 9. Again, this is assuming to take this path 1, 2 and a 6. This is assuming this path. But I guess 3 is storing this path, right? 1, 4, 1. This is 6 and this is 9. So definitely we will not take this 9. Definitely not. So you're not going to take this 9. It's a simple comparison you do and you see that you'll not take 9. Do we have any other adjacent nodes for 2? No, we do not have. We just had 1. So I can say that the job for 2 is also done. So once this is done, you move to the next node, that is node 3. Now is 3 infinity? Definitely not. 3 is not infinity. So we will take 3. So in order to reach 3, what is the distance that we took? We took a distance of 6. Now what are the adjacent nodes of 3? There are no adjacent nodes of 3 if you carefully observe. There are no adjacent nodes of 3 because there is no node to go, right? There is no other adjacent node. So I can say the job for 3 is also done. And once the job for 3 is done, yes, once the job for 3 is done, I can say my distance array, yes, my distance array is storing all the shortest distance from source 0 to all the source nodes, all the distance nodes, that is 0, 1, 2. You can find all the shortest distance to every node. So it was very simple. At the step 1 you find the topo sort, then you use the stack elements and you simply did a check. Whatever was this plus edge weight, if that's smaller you replaced it. I'll be showing you in the code, then you'll have a much more clarity. But as of now, I hope you have understood the entire explanation. Find topo sort, and it's a simple comparison algorithm on BFS that we are implicating to get our desired shortest paths. So if I discuss about the time complexity, the topological sort, as you know, will take big O of n plus e because the DFS takes that much of time, and since you're implicating another BFS kind of algorithm in order to find the distance, so this is appearing to be twice. So I can say the time complexity to be this, while I can say the space complexity to be big O of 2n if I consider the stack space as well as the distance array space. I'm not considering the graph storage space, that can be excluded because I'm just focused on the algorithm. So, and the auxiliary space complexity of the topo sort. If you are using a DFS algorithm, there will be auxiliary space complexity. If you're using the BFS algorithm, there will be no auxiliary space. So this will be the overall time complexity and the space complexity in order to find the shortest path in a weighted DAG. So let's discuss the Java solution. As I said, since it's a weighted graph, we are going to store it in pairs. So what I did was I declared a class of pair so that we can store pairs, and we are storing the node v as well as the edge weight, right? And we are having a constructor pair so that whenever we declare a class, it automatically gets assigned to that object. So this is how we do it in Java. We make a constructor, and I'm also writing two getter functions. In order, if we want to access the v or the weight, we can have a get v or get weight function which will give us. So as of now, what we have done is we have taken n equal to 6, we have hard coded it, and we declare an array list of pairs. If you can see, array list of pairs, and we have made sure that n array list have been added. This is the simple way. The only change is the pair that we are doing instead of an integer. Now you can see if there is an edge between 0 and 1, we are storing 1 comma 2, saying that there is edge 2 1 and the edge weight is 2. So we can simply call the constructor by new pair, which will create an object, and you can store it. So basically you will have the graph stored in this array list. Simple as the previous one, we just did pair, nothing different, we just used pair. Once you have done this, create an object of the function and call the function shortest path with the source node as 0, with the adjacency graph, and with the number of nodes as n. So let's look at the shortest path. So initially what you do, you have a stack, right? You have a stack and you have a visited array, as you know, in order to have the DFS function for topo sort. And you also have a distance array which will be used later. So we have this stack, we have this visited array marked as false, and now we call the function to print the topo sort. So this will be the function you can see in the top. It's a simple function where you mark everything as visited whenever you reach your DFS. Then you call DFS for adjacent nodes. and at the end when the DFS is over, you add that to the node. I'm not explaining in depth because I've already done it in the toposort class. So once you have crossed this line 37, I can say once this for loop has been executed, my stack will be having my toposort. So at the next step, what we did was we took that distance array, if you remember. After the execution of for loop, we made sure that the distance array has infinity values. So please make sure you have infinity values at every index, right? So once you have done this, please make sure the distance of source, because this is the source. Whenever you start with a source, that is assigned to be 0. Once that is done, it was very simple. You iterated for every element of the stack. So please iterate till the stack is non-empty, right? Please keep on iterating at every element of the stack. And you get the first node, which is right at the top of the stack. What is your first job to do? As you remember, you always check if that node has been reached. And in order to check that, you can say that if distance of node is not integer.max value or not infinity. If this is the case, I can say that the node has been reached previously, right? That is why it is not having infinity. Then you can iterate for all its adjacent node. Now the for each loop will have pair of it, right? Where it dot get weight will give you the weight and it dot get val will give you the adjacent node. So you simply know if you have required a distance of node till reaching node and the edge weight will be it dot get weight. If that adds up to give you something smaller than whatever is stored in the distance of the adjacent node, whatever is stored in the distance of adjacent node, if that is smaller, you just replace it. That's it. That is what we did. And you keep on doing this for all the nodes. Yes, you keep on doing this for all the nodes. And once you have done this, you can simply print your distance. If it's in max value, you can say the distance is infinity, or you can say it's unreachable. And if it is not, you can print distance of I, saying that it's still reachable by this much distance. So this is how the Java code will look like. You can find the code. I'll be leaving the link in the description below. So now let's discuss the C++ code. So you can see that initially I have n and m. So I've taken the inputs. Now instead of declaring an vector of int of adjacency list, we just declare a pair of int, so that we can store the adjacent node as well as the edge weight. And we have taken the directed graph and we have made sure that the input has been taken. After that, let's call the shortest path function with the source node. Yes, the source node is 0. So let's call the shortest path function. So when we go to the shortest path, what is our first step? To generate the toposort for the given graph, right? So what you do is you generate the toposort. You know, the toposort is generated by having a visited array and then having a stack and then calling toposort for every non-visited guy. I've already discussed this in the toposort video. So you can see over here, you go whenever you reach the DFS, you mark it as visited, then you traverse for all its adjacent nodes which are non-visited, and whenever the DFS gets over, you put it into the stack. Simple toposort. So once you have done this, right, what is your next step? In order to find the distance, you always took a distance array. So please take a distance array of n size, and we marked everything as infinity. So make sure you mark everything as infinity or a larger value. As in my case, I've done it as 1e9. You can do it as integer.max, whatever you want to do. After this, you know, to reach source, the distance that you will take will always be 0. So please mark distance of source equal to 0. After that, you just needed to iterate on the stack, if you remember. So keep on iterating till the stack is non-empty. Just keep on iterating till the stack is non-empty. And what you get is the first element, right? Every time you get the first element. So get the first element. What was the thing that you checked? If it is non-infinity. What does that mean? That basically means if that node has been reached previously. Yes, if that node has been reached previously, that is the meaning of that. If you have reached that node previously, the value will never be infinity. If you have reached, since it's a DAG, then only you can reach its adjacent node, right? So you traverse for its adjacent node. Now in order to get the adjacent node, that's it dot first, right? So you basically check current node distance, edge weight is it dot second. If both of them adds up, give a smaller distance than the distance at the adjacent node it dot first. You can simply replace distance of it dot first, because that is your adjacent node, with distance of node plus it dot second. Simply replace it. Once you have done that for all the nodes, what you can say is you can simply print this. If it is 1e9, that means that it's unreachable. You can print infinity. If it's not 1e9, you can print the distance, which means it is reachable via this much distance. So I'll be leaving the code link in the description below. You can check it out. So I hope you have understood the entire explanation as well as the code. So just in case you did, please make sure you like this video, and if you're new to our channel, do not forget to subscribe, right? And with this, I'll be wrapping up this video. Let's meet in the next video where I'll be solving other algorithms.
Whenever your heart is broken,